Recording in progress.
Okay, thank you. So I'm very happy to introduce you this today's speaker, Professor Ferdinand Plaschke from Institut für Geophysik und Extraterrestrische Physik in TU Braunschweig. And yeah, he's our law collaborator. In fact, he was in our institute, and but I would like to introduce him. So 2011, he took the PhD from TU Braunschweig, and then he went to UCLA for 2 years, 1 year, 2011 to 2012, and then you are our team members in the postdoc between 2013 to 2017, and then you get there also a bit. You worked as a lecturer from Wiener Neustadt and external lecturer also in TU Graz, and you got also therefore so habilitation from TU Graz, and then you get. Oh, you were until 2018 a postdoc, and then no, you were in University Graz, and then you studied. You were professor. You were appointed to the professorship in 2021. So we have now built a big group, and I think you will talk about observation and modeling of the dynamics magnetopause.
Okay, thank you very much. So yeah, I'm very happy to be here. I've brought this talk about observations and modeling of the dynamic magnetopause. So this talk will be about Earth observations and modeling then based on Earth data, especially from the THEMIS and cluster missions that are also very prominently used here in this institute. And I would like to mention that Niklas Grimmig and Lars Klingenstein have contributed quite a lot, actually with their work also to this talk that I'm about to give here. Okay, so let's start with the very basics, if I can actually move the slide. Yeah, I can move the slide. Okay. So first of all, we all know that the Earth, of course, has its own magnetic field, and if there were nothing else in the universe, then the dipole field would actually extend ad infinitum into space. But there is fortunately something different. We have the sun, and the sun does not only irradiate electromagnetic waves, so light, but also the solar wind, which is of course a gas of charged particles, so protons and electrons mostly, also maybe a couple of % of alpha particles, that are irradiated radially away from the sun. And now the question is, okay, how do these two things actually interact with each other? And we can model or actually think about this interaction in the following terms. What would actually happen if such a gas of charged particles would enter a half space with increased or some magnetic field, a geomagnetic field, for example? Well, if these particles would enter this half space, then of course they would be deviated due to the Lorentz force, and they would go out. They would kind of like perform half a gyration and then go out again here. And we can see that obviously due to the different sign of the charges, these charges are deviated in different directions, and so we have an electric current actually flowing here at the boundary between these two half spaces. And if we have an electric current, then that means that we also have a secondary magnetic field. And the secondary magnetic field actually accounts for exactly this difference in the magnetic field between the two half spaces that we have assumed to be there in the first place. So this is kind of like a self-consistent picture here. The other thing that we see in this picture is that the particles, they are kind of reflected from this boundary here, which we later will call magnetopause, which means that there's also a momentum transfer. Yeah, momentum flux is also pressure. So these particles are exerting a pressure on the boundary, which on the other side is then countered by the magnetic pressure. And this is exactly what is happening also at Earth's magnetosphere. So this is kind of a sketch what is happening in near-Earth space. We have here in blue the Earth, and then the geomagnetic field, which normally would be at further distances a dipole field. But then this is compressed here at the day side due to the incoming solar wind, due to the incoming electrons and protons. Yeah, and this is expanded then in the night side into a geomagnetic tail. And then here in gray we have the magnetosphere, with this the region of dominant geomagnetic field, and the boundary kind of between the solar wind plasma in this interior region is the magnetopause, which this talk will be about. So the magnetosphere is an obstacle to the solar wind. It has to flow around the magnetosphere, the solar wind. And this happens in this transition region, which is called magnetosheath. But the solar wind is also supersonic or supermagnetosonic in the frame of reference of the Earth. And that means that the information about the incoming obstacle or the obstacle ahead has to kind of propagate into the incoming solar wind. And in order for this flowing around motion of the solar wind to be able, a bow shock has to form here where the solar wind is decelerated, is heated, is thermalized, and then goes from Mach above 1 to Mach below 1, and then can actually flow around here. We see that the solar wind also carries its own magnetic field, actually the solar magnetic field, which is also called interplanetary magnetic field, which is draped then here around the obstacle. And then we see another region here, which is called the foreshock region. And that is because not all of the particles actually make it in the first place through the bow shock, but a few percent of the particles are actually reflected and then can move into this upstream region along these interplanetary magnetic field lines. So this is a region that is magnetically connected to the bow shock, and where then the reflected particles actually interact with the solar wind that is coming in, leading to all kinds of things that we will talk about in a few minutes. And then the magnetopause, last thing here, before I actually move to the next picture, you see here mu naught J equal curl of B. Of course, the magnetic field is changing here at the magnetopause, and that means that also a current has to be flowing there. Yeah? And the current is the magnetopause current, also called Chapman-Ferraro current, is part of a current system in and outside of the magnetosphere that kind of accounts in a totality with the magnetic field that is generated by this current system for the structure that we see, the global structure of the magnetosphere. This is the magnetopause current here at the day side, but also over the tail. This is kind of a 3D picture actually of the magnetosphere. And then in between here, these lobes, so we have like a northern lobe with magnetic field lines coming towards Earth, then southern lobe where the magnetic field lines go away from Earth. We also have curl of B, so we need a current sheet in between, which is called the neutral sheet current, which is also closed then with this tail current over here. And in general, we have then the entire structure of the magnetosphere given by this current system. Okay, so what is the magnetopause? The magnetopause is the outer shell of the magnetosphere. It is the outer boundary of the Earth's magnetic field, but this of course also applies to other planets. And the location, the basic location and shape of this boundary is just given by the pressure balance between dynamic pressure and thermal pressure of the solar wind plasma, and then the internal magnetic pressure. But since it is an outer boundary, it's also a gateway into the magnetosphere. So if we have particles or mass or energy going into the magnetosphere from the solar wind, it somehow has to cross the magnetopause. So the magnetopause kind of like is at a key spot or has a key meaning for the entrance of particles and energy into the magnetosphere. And energy is, or this entry is actually largely mediated by magnetic reconnection on the one side, and then waves and motion of the magnetopause on the other side. So let's have a look into these things. Okay, magnetic reconnection. What can we say about this? Especially when we have southward interplanetary magnetic field, so symbolized by this very big red arrow, we have actually a magnetic shear here at the dayside magnetopause. So magnetic field lines actually pointing in opposite direction, and we have this very strong current sheet. The current is of course maintained just by particles, going into certain orbits over there. And if for some reason locally this current cannot be maintained, then the magnetic field lines will actually reconnect. It can be kind of modeled by countercurrent, and then the superposed magnetic field of that missing current, together with the shear in the magnetic field, gives us a reconnected magnetic field lines. And this is what we can see here. You see these open magnetic field lines between which on the one hand side are interplanetary magnetic field lines, and then on the other side merge actually with geomagnetic field lines over here. And this open flux or open magnetic field is then transported to the night side with the solar wind flow, actually bringing in magnetic flux energy into geomagnetic tail, also particles, where then later on also magnetic reconnection can actually occur in the neutral sheet. And then we have actually injection of solar wind plasma into the near-Earth space or near-Earth magnetosphere. And this is like the most prominent way, this Dungy cycle, of entry of energy and particles there, and is actually responsible mostly, but not entirely, but mostly for many space weather phenomena. So here's just like an overview of what we can see. Of course, this is like the nice picture of space weather, yeah, the aurora, particle precipitation. We have a change in the magnetic field, and we have currents that are being induced, for example, in long landlines or so. So we can also have kind of like this picture over here, yeah, so like a burnt transformator picture somewhere in North America. Or also like this, SpaceX loses 40 satellites to geomagnetic storm a day after launch, because when you have particles precipitating in the atmosphere, then that also means that the atmosphere is heated and it expands. And these SpaceX satellites were actually just launched, so they were at very low altitude of, I think, 200 something kilometers. And so at that altitude, the density of the atmosphere was just increased suddenly due to the particle precipitation, and you have enhanced air drag of the spacecraft, and there were no means to actually save the spacecraft. They were just coming down. Okay, so this is also like an effect of space weather and of this reconnection and Dungey cycle, ultimately. And then you can have waves, for example, amplified by the Kelvin-Helmholtz instability. How does that work? Well, here along the flank, magnetopause, of course, we have high plasma particle velocities, maybe can be easily 400, 500 kilometers per second. And then inside we have maybe stagnant plasma, or at least severely diminished velocities with respect to the outside. And when we have these velocity shear over a boundary, and we have a displacement of the boundary, then of course here the particles have to be kind of a little bit faster maybe to overcome or to go around this bump. And so locally the pressure will be diminished, which amplifies also the change or the displacement there in the boundary, ultimately kind of like bringing these amplitudes of the waves up, and then leading to these rolled up vortices, which also can kind of like collapse and lead to plasma mixing and entry of particles into the magnetosphere here at the flanks. And of course the waves themselves also just radiate energy into the magnetosphere, which, for example, inside the magnetosphere can also couple to resonant magnetic field lines and induce some variations there in the geomagnetic field. And this does not only work at the flanks, actually the magnetopause globally, everywhere, is constantly in motion. It's really a very dynamic magnetopause, very dynamic boundary. And you can see kind of here, for example, these are observations from THEMIS E spacecraft over more than 4 hours, and you can see always where there are these like black stripes that we are crossing the magnetopause. Why can you see that? Well, inside the magnetosphere, we have kind of like a high geomagnetic field here, and like the red component, yeah, and a high particle energetic particle population. When we go outside into the magnetosheath, what we see is the thermalized solar wind. So this is the spectral energy flux density of the ions, yeah. So if we see here, this is kind of like particles that are mostly around like 1 keV, which would be like the solar wind line. This is kind of like spread out, and so you just from the color you can very easily distinguish between magnetosheath and a magnetosphere in this particular instance. Yeah, and so you see that the magnetopause is constantly moving out and in. Yeah, the spacecraft itself is just moving at very low velocities, maybe 1-2 kilometers per second. But the magnetopause is much faster. If you take some statistics, you can look down here at this plot. This is magnetopause velocity at the subsolar point. And this is just like a histogram, so you can see that 50 to 100 kilometers per second is a very common velocity for the magnetopause there at the day side. So it's constantly moving in and out, and the spacecraft is essentially staying still at the boundary, moving in and out all the time. And also the peak-to-peak amplitudes, like up to 1 RE, easily seen at the day side magnetopause. So that shows you that not only at the flanks, where we have the Kelvin-Helmholtz instability, but also at the day side you can see this in and out motion all the time. Okay, so what have we learned so far? The magnetopause motion is due, for example, to the Kelvin-Helmholtz instability. Yeah. Also, when we have southward IMF, southward interplanetary magnetic field, then reconnection is triggered. The magnetopause actually moves inward because we're kind of eroding magnetic flux at the day side. And of course, the most important thing is if the dynamic pressure changes in the solar wind, then of course this affects the position of the magnetopause very severely, because that is kind of like the pressure, one of the pressure component in this pressure equilibrium that determines where the average location of the magnetopause is. And if solar wind parameters change, for example in large-scale transients, yeah, like coronal mass ejections, or co-rotating interaction regions, or just normal solar wind discontinuities, then we also expect the magnetopause to actually move accordingly. But this is not the only thing. The other thing is also foreshock and related transients. So something which is occurring more locally near the bow shock or near the magnetopause itself. And here we have a couple of things that I will try to explain a little bit over the next slides. Hot flow anomalies, for example, foreshock bubbles, and magnetosheath jets, which also locally can lead to magnetopause motion. Okay, so how does this work? So let's first see what the foreshock actually is. Let's get back to this picture over here. Here we have the interplanetary magnetic field, and you see that this region over here, which is like slightly more orangey, is like magnetically connected to the bow shock. So particles that come in here and are reflected can move along the magnetic field into this foreshock region. Okay? And what happens is that this reflected particles and the incoming particles from the solar wind, they interact, and they can create a large scale, also large amplitude wave field in front of the bow shock. You can see this here in simulations. Yeah? So these are simulations from Van Alphen et al. These are Blasiator simulations, and you can see this extended wave field here in the density, simulated density, or also here in the simulated magnetic field. And these extensive and also high amplitude wave field also has severe repercussions to the bow shock and then to the downstream region. So the bow shock here will be actually quite undulated or patchy, not like very smooth. Yeah, if you go to with a spacecraft through it, you see kind of like a hard cut, but you see patches of thermalized and not thermalized plasma, for example. And this is found here downstream of the quasi-parallel shock. Quasi-parallel meaning because the angle between the normal to the bow shock and the interplanetary magnetic field is lower than 45 degrees. That's when we call it quasi-parallel. On the other side, quasi-perpendicular, it's more than 45 degrees. This is kind of like the quiet area. Yeah, the not so quiet area over here, you can see it in the wave field over here. And in this part, you can find, for example, magnetosheath jets. Magnetosheath jets are essentially just plasma bubbles, you would say maybe, where the dynamic pressure is higher than it is surrounding. It's kind of like a patch of solar wind plasma inside the magnetosheath. Yeah? And when this kind of high dynamic pressure bubble hits the magnetopause, then, okay, we already learned the magnetopause is a certain position due to the pressure equilibrium. We come with something like a high dynamic pressure. Obviously, it's like hitting the magnetopause with a hammer at a certain position, and so it will move inward, for example. Yeah, this has been observed, for example, here by Shu et al. 2009, magnetosheath jet, or here it's called fast magnetosheath flow coming in, and then creating a large-scale indentation in the magnetopause. It's kind of like an indentation, then you, of course you have a rebound also. And these jets can also start magnetopause surface waves because you have like a localized indentation, like a localized pushing in of the magnetopause. You change also locally the magnetopause current, and these additional currents have to be closed, can be closed, for example, by field-aligned currents, so you can have like also standing waves at the magnetopause being launched, or just surface waves that maybe later are amplified by the Kelvin-Helmholtz instability. So this is a very local phenomenon, and then you have also some more global phenomena, larger foreshock transients like hot flow anomalies and foreshock bubbles. And these are created when a tangential discontinuity, so a discontinuity in the solar wind essentially, interacts either with the bow shock, directly, or through the magnetic connection with the bow shock. So here at the hot flow anomaly, this tangential discontinuity intersects the bow shock, and plasma, that is hot plasma, can actually be sucked into this discontinuity and kind of like make a flow deflection here of the solar wind and completely change the pressure equilibrium also in the magnetosheath, leading to plasma and the magnetopause being sucked out here at this position of the intersection region. Another way is that you have the discontinuity not intersecting with the bow shock, but reflected particles actually filling a bubble just on the upstream side of the discontinuity with hot plasma, but very tenuous plasma. And this whole structure moves with the solar wind to the bow shock, and when it interacts then with the bow shock, you have also the pressure actually suddenly dropping, the magnetopause being moved out and then moved in again when kind of like this downstream region also is hitting this region. So large scale motion, sometimes local, here actually more global, that is produced by these two phenomena. And of course this is kind of difficult to capture in models, and not only to observe but also to capture in model, but these two things are of course interrelated. So what have we learned? A plethora of reasons keep the magnetopause constantly in motion. So there are many different phenomena that lead to the in and out motion of the magnetopause, and this motion is kind of important because it drives internal magnetospheric processes. So of course we can, by the motion of the magnetopause, we get energy of the particles into the magnetosphere, and it also connects different processes, for example foreshock processes, with something that happens inside the magnetosphere, like radiation belt dropouts and things like this that are kind of connected. It's a connecting boundary, so to say. So we are interested in that. However, there's a significant lack in understanding of this motion, and there's one specific reason for that, and that reason is that when observing the magnetopause, you can only observe it, the spacecraft, at the point where the spacecraft is. You're flying with your spacecraft and you are in the magnetosphere. Suddenly you find yourself in the magnetosheath. Then you know, at this point in space and time, I'm at the magnetopause. And then you lose track. And maybe the magnetopause comes back. Here was the magnetopause. But you are lacking kind of a global picture of it. It's only like specific one pixel events in space and time where you can observe the magnetopause, and to understand better how it moves, you need either many observations of these, or maybe some image that maybe will come to at the very end of this talk. So a very large data set is kind of necessary to improve our understanding. And that our standing is not very great, I actually show you in this very slide. So we start here in the solar wind, so this is very like with uniform energy, plasma in the solar wind. Then we cross into the magnetosheath, we cross into the magnetosphere, we have the high geomagnetic field, back into the magnetosheath, into the magnetosphere, back into the solar wind. And where do we observe this? Here. And what is from the models the prediction where the magnetopause should be? Here. And that is kind of like, I don't know, 4 Earth radii away. So it's kind of bad, okay? And maybe we can do better. So these are predictions by the Shu et al. Model, 1998 model, which is very popular. It's also a very easy formula, so to say, just depending on the solar zenith angle and the flaring parameter here. And it's just dependent on the dynamic pressure and the interplanetary magnetic field, Z component, north-southward component. So this is an easy model. Works actually amazingly well, despite of this pathological example. Okay, so how can we get a big data set? First, we need, of course, observations. We take this from THEMIS and cluster. THEMIS has more of an equatorial orbit. Cluster has kind of like a polar orbit, so we have kind of a different coverage from these observations. And then we also need solar wind observations. We take them from the Omni solar wind data set. And then we try a machine learning approach to actually get the magnetopause crossings. Because I can tell you, I did like a manual search for magnetopause crossings at the beginning of my doctoral thesis, and this is very tedious work. So, so if you have many years and many spacecraft of data, it's completely unfeasible. So you need some clever way of actually extracting this magnetopause crossings. And that's the clever way. Okay? Okay, don't look at this. Essentially what you do is you start with a very small data set of you manually pick the magnetopause crossings and then classify them manually. And classification means, am I in the magnetosphere or am I not in the magnetosphere? That is the classification. Yeah? And when I change this classifier, then that is my crossing, so to say. You can actually test or train and then test different machine learning models. You can choose the best model, which in this case is random forest classifier. So it's essentially you have different decision trees that you train with different random subsets, and then in the end you take a majority vote of all these decision trees, like do you think we are inside the magnetosphere or do you think we are outside the magnetosphere? And that also means that you get some classification probability out of this model. Okay. Then you go into a bigger data set, so you're from 2000, THEMIS data from 2000 to 2009, and when you do some visual inspection, you see that actually there are quite a few misrepresented crossings, and these are because, or classifications, and so you try to do also some threshold-based detection and try to classify things in the magnetosphere that are clearly in the magnetosphere and outside of the magnetosphere that are clearly outside the magnetosphere. And so with these kind of like reclassified results, you retrain the model, and then you go into the big data set, and you can of course test this with a test data set and so on, and in the end you end up with a magnetopause crossing database between 2007 and 2022. Okay, and this is published, this is work by Niklas Grimmich and I from 2023. And this is just an example of how this works. So this is just THEMIS data. From top to bottom we have the magnetic field, the velocity, ion velocity, ion density, temperature, and here the spectral energy flux density. And here again we can see where the crossings are. Yeah, we start in the magnetosphere, and then here we periodically cross actually into the magnetosheath. So going back and forth. Now let's actually convert the lower panel into a line plot by integration, yeah, so that we don't have to deal with so many input data. And then let's focus on one magnetopause crossing, and then here you see the discretized version of all of these parameters. So the 5 panels above are exactly the same parameters, and here you see the label. So we start, actually we go here from the magnetosheath back into the magnetosphere, and the label tells us not in the magnetosphere, not in the magnetosphere, now we are in the magnetosphere. Okay? And then there is some classification probability attached to it, and then you can kind of combine these probability to say something about the probability of the detected magnetopause crossings. And here it is very nice, but then there are also, of course, detections of the magnetopause crossings with a lower probability overall. And this is actually what the algorithm then detects. So it has very nicely detected here all the magnetopause crossings, and these end up in the database at the end. Okay. And if you combine this with the THEMIS data, or you apply this to THEMIS, you apply this to cluster, then this is the coverage that you get here for THEMIS. Only the day side was considered. So here you see kind of like a color density plot of where the crossings have been found. And then this is here for cluster, and you see that for cluster, actually, if you just take the data, you will also find quite a few magnetopause crossings inside the magnetosphere, but Niklas actually checked those. These are all low probability crossings. So this is something where the algorithm itself said, I'm not so sure if this is a magnetopause crossing, and in fact, these are not magnetopause crossings, yeah, but of course, for completion, this also have to be included in the data set. And at the moment, we have a student assistant actually going through these lists and then trying to validate and improve the student magnetopause data sets. And then you end up with over 100,000 magnetopause crossings from THEMIS, and then close to 40,000 magnetopause crossings from the cluster mission. And these are all published. So these are usable, published in Grimmich et al. 23 and then so 24. Okay. Few simple statistics of these crossings. So where do we see them actually, and what can we infer from this? Well, in these panels, let's see what they are. So this is in blue. We have all magnetopause crossings. This is the only THEMIS results. In red, we have just subsolar magnetopause crossings. So those that are seen just around the nose of the magnetosphere. And then in green, the ones that we have been identifying at the flanks. Yeah, so this is like a equivalent magnetopause standoff distance here, and then if we compare this with the Shu et al. Model, then we get a standoff distance variation or deviation from the model, and then we can see, okay, what is the spread actually around the model? Yeah, and we can see also from this, just from this database, that there are quite a few crossings here that are quite far from the model. Yeah, so this is in RE. So here, would be extreme deviations, 1, 2, 3, 4 RE away from the actual model. Yeah, and it goes both ways. Actually, in the subsolar region, we see more expansions. These are these positive deviations. So the magnetopause is further out. And then on the other side, we have the compressions. So the magnetopause is further in, that we have actually been thinking just based by the model. Yeah? And then we can also look, for example, as a magnetopause crossings per hour, just as a matter of longitude angle, and also see that, for example, at the flanks we see more magnetopause crossings, probably because there we just have the Kelvin-Helmholtz instability that's driving the magnetopause in and out, and then leading to more magnetopause crossings.
Yeah, okay. The model has only one value for the position, yeah? So
no, so for each crossing there's a unique set of solar wind conditions, which means that the model will predict a certain location of the magnetopause. But this is then here always pointed to 0. So this
it's not a time-dependent model, which would also maybe give you some variance, yeah, when you just let it run.
Yes, it will give you, it is kind of a static model in the sense that each solar wind condition leads to one magnetopause location. But of course, as the solar wind changes, then the model will also predict different distances of the magnetopause from the Earth. So, but that's the only time dependency. There's no, like, let's say, intrinsic time dependency in terms of a ripple in the magnetopause moving along the flanks. This is not included in any of the models that exist so far. Okay. We can also do some statistics with this, of course. For example, we can see that the IMF cone angle, the cone angle, by the way, is the angle between the interplanetary magnetic field and the Sun-Earth line, how it influences the subsolar magnetopause distance. And you can see that low cone angles over here actually lead to large expansions of the magnetopause. Yeah? So this is here in orange. Here it means expansion of the magnetopause, probably related actually to these foreshock phenomena that I was talking about. And also the solar wind velocity actually has a major influence on the magnetopause, extreme magnetopause deviations. So here is the solar wind velocity starting from very low, 300 kilometers per second solar wind, up to here 800 kilometers per second solar wind. And with these higher velocities, we see that both the compressions and the expansions become more prevalent. And that is, for example, due to Kelvin-Helmholtz waves, so we have larger amplitude waves being created, but also maybe due to hot flow anomalies and foreshock bubbles, because when you have a higher velocity solar wind, this also means more particles are being reflected into a foreshock, and you have kind of like a stronger, more prevalent foreshock phenomena that can be observed here. Okay. So we see many magnetopause deviations, also extreme deviations, extreme expansions, extreme compressions of the magnetopause when comparing them to the model. And now the question is, of course, well, how good can these extreme deviations actually be modeled? How good can actually the location of the magnetopause be modeled? And can the actual models that we already have be improved? So let's have a look at that. Okay. Here are a small overview over 4 of the so far existing models. So here we have the Shu et al. 98 model, which is very prevalent, very widely used in the community, but also other models, Lin et al. 2010, Liu et al. 2015, and Nguyen et al. 2021. All of them include the dynamic pressure. It's an input parameter, which is the most important parameter. They also include, for example, here the BZ component of the interplanetary magnetic field. Some of them actually include more components of that. Some include the dipole tilt. So there are differences in the models. What you can observe from these models is that over time, there's a clear progression in the complexity of this model. So over time, obviously, people try more and more things, and the models get increasingly more complex over time. And so you would think, okay, they get more complex, they also should get better over time. Yeah? So do they do this? Well, actually there are some differences, of course not like huge differences between the models. You can see this here in 3 planes actually, just some line plots for certain magnetic field upstream solar wind conditions. Some of the models include the cusp regions here, the indentations where the magnetic field goes inward towards Earth. Yeah? And then the Schuh model doesn't, it's completely symmetric. But other than this, you see some similarities definitely between the models. Now, how well do they fare? Okay, so let's compare this for the subsolar region. Yeah, solar zenith angle below 30 degrees. We're just looking at the subsolar region plus minus 2 hours in local time. From the huge cluster and THEMIS data set, then 33,000 magnetopause crossings remain. We can use that for the testing. And then we find that all the models actually perform more or less equally good or bad. So we have here the Schuh model, the Lin model, Liu and Nguyen. And if we compare the root mean square error, we get 0.88, 0.82, 0.90, and 1.06. So they are all more or less the same, maybe even a little bit worse. So, and the question is, okay, can we actually do better than that? And so one thing that we can do to see why this might be the case is to train a regressor model, a machine learning regressor model, and then obtain the so-called SHAP values for each of the magnetopause crossings to contribute to assess kind of like how much each of the parameters that go into the model contribute to the final output. And which parameters, I will explain this a little bit more in a minute, which parameters can be used as input. Well, we can use here everything in blue, which has already been used in former models. Yeah, dynamic pressure very prominently, magnetic pressure, IMF cone angle, the clock angle, I don't know, the dipole tilt. Yeah, this has all been used, but we can use also many more, like internal magnetospheric models. The AE index tells us how much substorm activity is going on in the magnetosphere. Yeah, Dungy cycle reconnection related, so to say. SIM-H index is an index of how large the ring current is actually at the moment around the Earth. Also, also related to this, related to geomagnetic storms or geomagnetic activity. Then F10.7 flux, completely unrelated. This is like a proxy for EUV flux from the sun towards the Earth. You would say, why should that actually play a role? And that's actually not entirely clear why it should play a role. But if you have EUV flux hitting, of course, the atmosphere, then you will have, for example, heating of the atmosphere. You might actually have increased conductivity in the upper atmosphere that then plays also a role in the magnetopause, has a repercussion on the magnetosphere, plays a role on the magnetopause location. And then you can include other things like solar wind speed, temperature, alpha particles to proton ratio, and so on and so forth. And if you do that, all of these input parameters, put them into a machine learning model, and then try to figure out what the contributions are, then you get a picture like this. And these are the SHAP values. So what are these? This is based on Shapley values. Shapley values are a concept from cooperative game theory, and it's kind of like an analytic method to understand how much in a cooperative game, how much each player playing in a team contributed to the team's outcome. Yeah, it's essentially, you have, I don't know, a team of 3 people playing in the contest, and they win 10,000 euros, and then you want to figure out a fair way to distribute the 10,000 euros to the 3 people in a fair way. How do you do that? That is what Shapley values actually tell you. Now, this is an analytic theory. The problem is that this depends in a factorial way with the number of parameters that you are dealing with. And so this is not good for machine learning. So SHAP values is kind of like the same theory applied in a manner that it is computationally feasible to determine, let's say, with some sort of like Monte Carlo simulation method. And in the end gives you the contribution of a single parameter to the total outcome of the model. So here the SHAP value is in RE, yeah, and here you have different parameters. And each magnetopause crossing from the model gives you a prediction. No, magnetopause should be here in the subsolar region. And based from the, let's say, mean value of the magnetopause, it means, okay, the dynamic pressure contributes this much. Then the next parameter brings us back to this place. And then the next parameter brings us back here. Yeah? So you have like different contributions, and adding them all up leads to the magnetopause location where it is predicted. Okay? So each point here represents one crossing and one contribution of this parameter, one contribution of this parameter. Then here color-coded you have the parameter or feature value. Yeah? So for example, high dynamic pressure, here in red, means negative Shapley values because high dynamic pressure bring the magnetopause inward. So reduce the distance to the Earth. Yeah? If you have low dynamic pressure values, you have high Shapley values, they bring the magnetopause outward, yeah? So they increase the distance, and so on and so forth. And then when you take all of these Shapley values of the individual parameters and compute the mean, the absolute Shapley value, or Shap value, you get a parameter importance, okay? And this list here is actually ordered by parameter importance. So what is the most important parameter? Well, not surprisingly, it's the dynamic pressure, obviously. Yeah? And then the next one is AE. And that's interesting because this has not been considered so far. So it's an internal variable of the state variable of the magnetosphere. And the next one is SimH, and then we have F10.7. And everything that has been considered so far is actually down the list. So that's an interesting result, isn't it? I mean, the problem, you have to take it with a grain of salt, because if you have correlations between the individual parameters, this can also lead to a redistribution of the Shapley values kind of internally, unintentionally. But there's a way to kind of test this, if this works or not. So, and the way to test this is we take these 6 parameters here in green. We take F10.7 out because it's kind of machine learning model just for the subsolar region and see how it fares. And you remember we had root mean square errors of the traditional model of 0.8, 0.9. This one gets 0.68, which is significantly better. You can also just take the magnetopause crossings and do no machine learning, just these input parameters and the locations of the magnetopause crossings, and just make a second order regression, yet a multivariate regression, no machine learning involved. You get 0.72, still much better than the current. Yeah? And the coefficients that you get are shown in this table over here. So here, this has to be read as follows. This is kind of like the base subsolar distance of the magnetopause, and then you add normalized values with these coefficients. So essentially you take the individual parameters, subtract the mean, divide by the standard deviation, and then put in front these coefficients. These here would be the linear coefficients, and then all of these would be called the quadratic coefficients. So for example, this 0.06 would be plus 0.06 times P dun squared, and this would be plus 0.04 times AE times P dun, and so on. Yeah? So you get like a quadratic or second order model with like zeroth order terms, first order terms, and then quadratic terms over here. And yeah, and still it's pretty good. And actually, if you just take out the red coefficients because they are so small, this almost changes by nothing. So it's the same value. So you can even reduce the complexity of this quadratic order model and still get actually quite good prediction capabilities just for the subsolar distance. And so if you then do the comparison of models, so we have here the Shu model, the Lin model, and then this custom support vector regression. This is actually a machine learning model that we had, and then the polynomial model, so just the quadratic order model. Then you see that, and test it actually on an independent data set, just to be sure that it's not like a training issue, you know. You still get, yeah, these root mean square errors of 0.66 and 0.69, which are much better than the traditional models. And this brings me to the conclusion slide. So I hope that I could give you an impression that the magnetopause is actually a quite highly dynamic magnetopause boundary. It's all the time in motion. at the flanks, but also in the subsolar region. And sometimes it is so much in motion that it actually leads to extreme compressions or extreme expansions of the magnetopause beyond what the current models predict. And we can gain some insight with big data sets and some machine learning techniques to understand actually, or to capture more of this variability, for example, in the models, and then we have less variability to explain maybe, for example, by local phenomena, like local impact of a hot flow anomaly. It's very hard to capture by a global model, or impossible essentially. Well, never say impossible. Hard. Let's say hard to capture, okay? And so this is what we have tried to do here, and again, the work that has been mainly done for the later part by Niklas Grimmig and by Lars Klingenstein. So the magnetopause models are published by Grimmig et al. 23 and 24. And Lars Klingenstein actually got today the preprint published in Annales Geophysik about the machine learning, the last part essentially, the machine learning model and the polynomial fit in the subsolar magnetopause. So this is also now out there. You can read it by yourself, of course. And we hope that these efforts that we are doing in bringing these large-scale data sets and also the models into the scientific community, that they can help in further studies in preparation, for example, of the ESA SMILE mission. And why is this so related? Well, I said in maybe 20 minutes ago or so that one of the problems really is that you can only observe the magnetopause at the moment if you are at the magnetopause at one point in space and time. Yeah? But of course the SMILE has a large soft X-ray imager, and there's an effect, an interaction, charge exchange interaction between the Earth's exosphere and the solar wind plasma. And these photons that are being created by the interaction, they are actually captured by this imager, and the hope is that maybe in 1 year or 2 years we can actually capture these photons coming from the region near the magnetopause, and by contrast see where the magnetopause actually is lying and see how it is moving over time. It's not a good time resolution, but it would be actually groundbreaking to get kind of like a video of this magnetopause motion, and then hopefully we can connect what we see in this imaging results with the results that we are getting with these efforts. Thank you very much.
Questions?
Ask.
Yes, please.
Just ask some basic setup of this modeling. All mini data for SOLID-1. What's the data resolution?
For the data sets, for the modeling, I think it was 1 minute to check it back to 1 minute.
Okay, then this 1 minute for SOLID-1 data. Then for the THEMIS data, cluster data, you may identify the multiple crossing. Sometimes multiple crossing. What's the minimum time? For example, if you have one crossing, next crossing happens within 30 seconds. Do you count as 2 crossing or 1 crossing? Do you have some minimum term? At least every 5 minutes you count as 1, or if within 5 minutes there are 20 multiple crossings, do you have 20? So this is the thing.
I think in this it is counted multiple times. This is also a problem for the modeling if you want to count.
Minimum distance, time.
12 seconds, I think, is the minimum distance. 12 seconds, I think, or 24 seconds, I think, is the minimum distance, because 12 seconds is the resolution.
And then you have some problem. Then let's say within 1 minute you have 5 multiple crossing. Then you have 1 SOLID-1 condition. SOLID-1 condition corresponding 5 different crossing. And once I have different crossing, obviously something changed. Obviously something changed, right? That's why I have multiple crossing. But then you have only 1 SOLID-1 condition.
Yeah, but of course the 5 crossings are essentially just 1 crossing because they observed essentially at the same spot. So it's the same solar wind condition corresponding to the same location where this is being observed.
That's the trajectory of the spacecraft.
But the spacecraft trajectory is completely irrelevant for this, because it's like 1 kilometer per second or so what you have for a near apogee. So you have like 60 kilometers, maybe 100 kilometers that the spacecraft have been moving, if it is radially moving, which oftentimes it isn't if you are kind of closer to the apogee. So, but there is a point actually to this. and that is that if you do the training, for example, if you have rare solar wind conditions, or you have like extreme magnetopause crossings where you have maybe just 1 or 2 crossings further away, then these are severely, let's say, underweighted in the model. So it's, and in order to capture them, maybe you have to do some like different weighting or a replication of certain crossings that are at like pathological positions.
We move someone, maybe minimum 1 minute. Seem like so.
Yeah, maybe that's actually a thing. But actually, the one thing is also a thing that was tested by Lars was to look for temporal changes, actually, or temporal, let's say, you retard, for example, the solar wind input into the magnetopause crossing. So you don't take, for example, solar wind from the crossing time itself, but from 5 minutes before or half an hour before or something like this. And this doesn't influence actually the model much, because there's another thing, of course, which is not captured if you take instantaneous solar wind conditions, and this is the propagation of the solar wind from the Braunschweig nose, where the Omni data set is kind of like calibrated or made for, to the actual magnetopause, where the conditions then have to determine whether magnetopause is seen. So this is another thing. And another thing which is also important for this is that the Omni data set is sometimes not extremely precise or very reliable. So you see, for example, sometimes major differences between what was observed in the Lagrange point 1 and then is propagated to the Braunschweig nose, to what is locally observed, for example, at the Braunschweig nose if you have a spacecraft there. But that's a different story.
Have you considered gradients of different physical quantities in the solar wind?
Gradients with respect to what?
For example, if you have 1 minute data from Omni, the gradients you can calculate, for example, temporal differences. And when the solar wind is highly variable, then those differences increase, and that can also influence the training.
I think Lars has been testing things like this, but it's not included in the paper that is available as the preprint. So I'm not entirely sure if this has been tested, but if not, then this would be a very nice thing to actually look at and include here. Yeah.
I found it's really great that this last statistics, because this shows the essence of the solar wind magnetospheric interaction. Because the previous models, your Schuh model, you just think, okay, solar wind drives everything and determines the place. But now you have very clearly shows that no, you need the internal feature. Ring current, most likely US image, and the aurora index is most likely line current. So all the processes in the magnetosphere you need to include in order to understand the balance, this very simple balance. So the time scale is different, you have to understand the process. So it's very nice to show it's that the planet is determining the solar wind magnetospheric interaction. It's not driven. Mostly interesting to check. Of course, we don't have ring current so easily, but Mercury would be interesting, you know. This is another source where you can see, again, this kind of study and see how much you can explain everything with the solar wind parameter, or you still have some internal parameter. Which
Of course, Mercury, first of all,
you don't have feeder current, ring current, so you need to do
you have nothing.
induced current or whatever. You have to think about other parameters, but at least how much can a planet do against the solar wind is something this is showing. So
yeah, exactly. So there's
some other planets do the same way, simply.
It shows that the internal state is important in determining where the magnetopause lies. And I mean, we know that kind of in comparison, for example, if you take Jupiter, is like, I think, a prime example, because at Jupiter you have a rotation speed or rotation period of 10 hours, which is really fast for such a big planet and for a huge magnetosphere. And then you have plasma inside the magnetosphere from Io, which is kind of like accelerated to co-rotating speeds mostly inside the magnetosphere, and due to the centrifugal forces kind of like pushing from the inside.
Yeah.
So there, it's not internal magnetic pressure alone, but also internal particle pressure that's kind of like driving the magnetopause outward from what it would be if it just would be internal magnetic field of Jupiter and the solar wind dynamic pressure. And there the difference is huge. I think it's like predicted as like 30 Jupiter radii, and in theory it can be like 60 to 100 Jupiter radii. So it's the difference is kind of huge. But at Earth you can also see it.
Yeah.
However, I want to make one more point actually about the internal state variables. There's also a reason why you don't want to use internal state variables for certain magnetopause models, and it's of course if you have to rely on the internal state, it's hard to use it as a prediction value.
I know there's a reason, but on the other hand, that's why you have to understand, and to do the real prediction, you have to use, so this is the evidence that you have to understand internal process to do good
I mean,
prediction.
the F10.7 flux, that is the ring current. No.
This is the ionospheric, yeah.
Probably the current, field line current also.
Yeah, so field and current matters, of course. So that shows you. So if you need something more, it's this paper.
Absolutely.
So just last one.
Yeah.
These indices that represent the internal state, are they measurement based or model based?
They're measurement based. AE is based on ground magnetic field variations in the auroral oval region. So it's from ground stations essentially, that you see like the ionospheric currents. SIM-H is a high cadence version of DST, and DST is based on disturbance storm time index, and this is based on equatorial magnetic field measurements. So if you have a ring current, essentially this ring current of course also makes a secondary magnetic field that overlays with the internal magnetic field of Earth and reduces the northward component of the magnetic field in the equatorial region. And if you have like quiet times, it's like at a certain value. If you have storm times, high ring current, it drops down, and for severe storms maybe below 100 nanotesla, maybe minus 500 for very severe storms, and then it kind of recovers over days. And this is
Can I?
Sure.
I think Ali was.
Thanks very much for your talk. I didn't know any of these recent works done, so thanks for educating. I have to read them, but maybe if you could give me something here. Have you tried to remove the known factor, which is the dynamic pressure? So I think in summary, you're trying to say the magnetospheric content adds to the kind of this dynamic that the planet is standing off against the solar wind. So if you remove the magnetic pressure factor, which is the most dominant one in the Schum model, then does your machine learning can say that if you can create a factor that talks about the planetary content response, so that might affect both the AE and the things and all of them, which are maybe there's a direct correlation between how the planet is more filled up, these factors might go forward.
Okay, so what you say essentially is we take out dynamic pressure, and then we do like, let's say we train another model, we do just regression just with the other parameters. Okay. I think no, we have not done yet. So this is one thing, because obviously we go in with the idea that dynamic pressure just from basic physical understanding should be the main driver. Of course, I mean, here you get the coefficients, just the linear coefficients, for example, of AE and SIM-H. I'm pretty sure that if you take dynamic pressure out, is what you would do is you would kind of, the model would try to redistribute this to some other factors and try to cover it with other parameters in this. It's a good question. I don't know. I think we have to test, essentially. Yeah.
Okay, first Zoltan and then.
So-
yes, okay.
if the dynamic pressure is important, and it has to be important, what if you do not consider the dynamic pressure, but instead of it, the density and the velocity? Will the model find that actually it is the density and v square are important or not? This is one question, which is indicating that if the model will not find separately for density and velocity the importance of the dynamic pressure, we could have another combinations of parameters in the solar wind. If we do not consider those parameters can be hidden parameters for the model. However, internally the magnetosphere is observing them.
Okay, so I cannot talk about not including the dynamic pressure in the model, what comes out, because I think we haven't tested. So this is the first thing. But the second thing is, what Lars has tested is to include velocity and dynamic pressure with the dynamic, velocity and density with the dynamic pressure. And in this case, the density doesn't matter, but the velocity works in the opposite direction, just linear velocity. Which is also interesting why it would be the case, but this is what then comes out of the model. It kind of like takes out a little bit of the contribution of the dynamic pressure itself, just the linear term.
Okay, Martin? Martin?
Yeah, so you mentioned it already that you can kind of compare those machine learning things with simple regression models, and you get still good results. So, and you also showed like a ranking of importance of the parameters, right? So this screams at me like do a principal component analysis in that sense, and you would maybe you would also get some sort of a ranking of those, right? How important which parameter is, but just in a purely linear way.
The question is, what would you take as the base value? Would it be just deviations from the model, maybe? Because the question is,
I mean, you would probably also see as the first most important axis, basically how, what parameter explains your variance best, so in which way.
Principal component.
Principal component analysis with, let's say, deviations of the, because you need something to simulate the variability, but it would be then, for example, delta R naught or something like that. Yeah. That's something that can be tested.
I have a slightly philosophical question, maybe. So when I listen to your talk, it seems like, the models get more and more complex, but they actually get worse. And so you put all the efforts into, say, very well defining your parameters, how to measure them, and then making clear what the model should be, so the kind of outputs and inputs. And then you forget about all the rest, right? So, I mean, classically, if something is not fitting, then you would try to improve your plasma equations. You would say, okay, maybe in this case, my order is not good, what to do? So this is the classical approach. Now, with this machine learning approach, I think it's kind of dangerous that we forget about all the physics. We are only discussing parameters and output. And I think in the end, is that really what we want?
I mean, with machine learning, there is, of course, a tendency to take it as a black box. I mean, machine learning has many applications, and it's nice you can treat large data sets with it, but of course, it is, once you have a trained model and it's performed, let's say, decently well, you don't know what the connections are between input and output, what the model is actually giving you. The Shep values stands actually for Shapley additive explanation, so you add kind of like the contribution of the different parameters is, I think, one of the ways to try to make it less black boxy, to try to understand what the model is actually doing. So we are using this approach to get with the importance of the individual parameters, and then maybe even forget about the machine learning approach and do traditional multivariate regression. Yeah, but of course, for maybe more complex applications where regression is not possible, or where such an analytical approach fails and you are doomed to take maybe the machine learning approach, it is of course important to still at least make an effort to try to understand what the physical relation is there, because otherwise we are kind of like detached from a physical explanation and from trying to explain what is going on. We are just using the data, let's say, in a generic format. And I think it should be our effort to try to explain how things are going and not only to predict what maybe the outcome of a certain input parameter set should be.
Yeah. But in this case, you know exactly what you did as input, right? And the outcome was quite clear. This AE or SIMH has already kind of meaning. For example, SIMH tells us that, okay, ring current, which means energetic particle behavior, is very important, or pressure has to be very important to include it in a magnetospheric model. That means if you do just somehow very cold plasma or general Maxwellian plasma and do MHD and predict this magnetosphere behavior is wrong. This tells
So what
tells us.
you are saying is that it needs a good plasma physicist to actually define these input parameters.
Yeah, of course.
You need understanding,
that's
put
what
in.
I'm saying. What do you want as a parameter? You cannot put anything, right? You cannot put any whatever.
In the machine learning, you could put anything.
You can put anything. Yeah, you can put anything, but you have to choose already and kind of. It's useful, and then you can. This will confirm your physical thinking.
Sorry, if you mentioned the velocity, the velocity through viscous type interaction can introduce magnetospheric activity over longer time scales than the time scale of substance. And if something is changing internally because of the viscous interaction, you have the internal parameters in your model. So it could also, the velocity, so viscous interaction can change the physics.
Okay, yeah.
So, like, have you thought about trying to discover some kind of like a functional relationship between the magnetopause location and all these parameters?
Yeah, the functional relationship is kind of this second order regression, right? So these are the coefficients. I mean, you have to normalize the input values, of course.
These are the numbers that you see are, like for example, if I look at like the AE times the dynamic pressure, like, I mean, that's not like very significant, for example. So like, would that appear in your equation at all or no? Like, it has a small value, I know, but I'm saying like, can I write down an equation, for example? Like,
I mean, these are the coefficients of an equation. So you would start with like, this is the zero order term, then you start with, these are the linear terms, so minus 0.8 per dien, minus 0.3 AE, and so on.
Okay.
Then you start with the quadratic terms, plus 0.06 per dien squared, plus 0.03 AE squared, and so on. And then you have the mixed terms in between.
Okay, so yeah, okay. And have you tried to look at like the correlations between these different parameters, because all of them are not independent, obviously?
Yeah, I mean,
Principal component analysis.
principal component analysis, but of course there's not 100% correlation between them. It's just, and sometimes it's also like time shifted or so, especially with AE, for example, in relation to BZ and things like this. So there's a complex interrelation between parameters which has to be explored more. I mean, this is like a first try, and I think it's great for a first try, but there's a lot of work to be done and to disentangle the individual correlation. Because at the end of the day, I mean, you have the input parameters. If you take just the solar wind plasma, let's say, you have, of course, all the moments of the distribution function, you take that, but then what happens in this complex system of the magnetosphere, where you get all the other parameters, that's a totally different story, which goes into probably, I don't know, 70, 80 years of magnetospheric physics history, and which is not a complete picture yet by no means, so it's just like scratching the surface. So there's a lot of work to be done to actually disentangle that.
Yeah, I do have one question about the relationship between the magnetopause crossing and the F10.7 index, because all the other parameters actually is the I mean, it's a kind of a process that solar wind affects the magnetopause, and then the other process, the subsequent process will affect all the others, the index such as the AE and CMH or something else. But the F10.7 index is the represent the present activity of solar activity, right? But that is the future things that can affect the magnetopause, right?
No, but F10.7, I mean, F10.7 is the radio flux at 10.7 centimeter wavelength. Yeah, and this is traditionally, this has been used as a proxy for extreme ultraviolet flux from the sun, because extreme ultraviolet is all like blocked by the atmosphere, is all absorbed in the atmosphere, and from the ground you cannot observe it. You can observe it, of course, from space, but F10.7 has been used as a proxy for this. But of course, when we talk F10.7, we are talking about flares, for example, contributing to the EUV flux that is then absorbed at the atmosphere. And the way probably that this is contributing to the magnetopause distance is by increase in the conductivity of the ionosphere, and then ionospheric and then field line currents being closed more easily through the ionosphere. I mean, this is because there has to be some current relation that then leads to magnetic disturbances that add up to the magnetopause distance.
So this closure of this current, of the field line current, modifies, of course, the magnetic field at the magnetopause balance, and so this is interesting.
Okay, thank you.
Right. Okay. So that's good. Yeah. Thank you very much, and thank you for the audience.